Welcome! In this session, we will explore an interesting problem called rotating the box. We'll go through the problem statement, analyze potential solutions, and understand the most optimal approach step by step. Let's dive in. In this problem, we are given a 2D array that represents a box. Each cell in this box can hold one of three types of values: a stone, represented by the character hashtag, an obstacle, represented by asterisk, or empty space, represented by dot. The task is to rotate this box 90 degrees clockwise and simulate the effect of gravity, which causes the stones to fall to the lowest possible positions within their columns. Stones cannot pass through obstacles, and empty spaces allow stones to fall. The output we need to return is the transformed 2D grid after applying both the rotation and the gravitational effect. The output of this transformation should be another 2D grid that shows the final state of the box after it has been rotated and the stones have fallen. To illustrate this, let's look at an example. Suppose the input is a box with one row and three columns, represented as a list of lists, hashtag, dot, hashtag. After rotating the box clockwise and letting gravity take effect, the stones fall to the lowest possible positions. The output for this example would be a grid with 3 rows and 1 column, dot, hashtag, hashtag. To further explain the previous example, the initial box had 1 row and 3 columns, hashtag, dot, hashtag. When the box is rotated 90 degrees clockwise, each column becomes a row. Then, gravity causes the stones to fall to the lowest positions within these new rows. So, the first column, which contains 1 stone, falls to the bottom row. The second column remains empty, and the third column, which also contains 1 stone, falls to the second row. This results in the final output grid of dot, hashtag, hashtag. Now, let's consider a slightly more complex example where the input box has 2 rows and 3 columns, hashtag, asterisk, dot, hashtag, hashtag e asterisk. The output for this transformation is a grid with 3 rows and 2 columns, hashtag, dot, hashtag, asterisk, asterisk, dot. Here's how this transformation works. First, when the box is rotated clockwise, the first column becomes the first row, and the second column becomes the second row, and so on. Then, gravity is applied to each of these new rows. In this case, after the rotation, the stones in the first column fall downward to the lowest positions in the first row. Similarly, in the second column, the stones fall downward, but they are stopped by the obstacles. Obstacles remain fixed in their positions and block the movement of stones. The third column, which only contains an empty space, simply rotates into the new grid. This process results in the final state of the box, hashtag, dot, hashtag, asterisk, asterisk, dot. Lastly, let's consider some edge cases. If the box contains no stones, the output will simply be a rotated version of the obstacles in empty spaces. In the case of a box full of obstacles, no stones will move, and the result will again just be the rotated structure of the input grid. For boxes with only 1 row or 1 column, the behavior is straightforward. With 1 row, stones simply fall to the bottom after rotation, and with 1 column, the box remains unchanged since rotation doesn't affect its structure in this case. To begin, one of the initial approaches we explored was the brute force method, which involves simulating the process in 2 distinct steps, applying gravity to the stones in the original box and then rotating the resulting grid 90 degrees clockwise. This means we first move all the stones, represented by hashtag, to the lowest available positions in each row, ignoring any obstacles, which are represented by asterisk. Once gravity has been applied, we rotate the modified grid by transposing it and reversing each row to achieve the final result. While this approach is straightforward and easy to implement, it requires creating an intermediate grid to simulate the gravity step and another grid for the rotation, making it less efficient in terms of memory usage. The time complexity for this method is O(m*n), where we iterate over all grid elements multiple times, and the space complexity is also O(m*n), due to the need for an intermediate grid. Although simple, this approach is not ideal because it separates the 2 processes, leading to redundant memory allocations. An optimized approach improves on the brute force method by combining the gravity and rotation steps into a single process. Instead of handling these steps separately, we calculate the final positions of the stones in the rotated grid directly as we iterate through the original grid. The main observation here is that in the rotated grid, a row from the original grid becomes a column, and gravity in the original grid corresponds to filling from the bottom of that column upwards. By iterating through the original grid bottom to top and simultaneously updating the rotated grid column by column, we can simulate both gravity and rotation at the same time. The process starts by initializing a rotated grid with dimensions nxm. For each row in the original grid, we track the next available position in the corresponding column of the rotated grid. Stones are placed in the lowest available positions, while obstacles are placed directly in the rotated column and reset the available position. This eliminates the need for an intermediate grid and reduces redundant computation. In terms of complexity, the optimized approach achieves a time complexity of O(m*n), as we still iterate through all grid elements once, and a space complexity of O(m*n) for the rotated grid. However, the efficiency comes from combining the gravity and rotation steps, which eliminates the need for an additional intermediate grid. This approach is slightly more challenging to implement as it requires careful management of indices and destination positions during the iteration, but it avoids redundant computations and unnecessary memory allocations. This makes it a more refined and efficient solution compared to the brute force approach, as it leverages the relationship between the original and rotated grids to streamline the process. The optimized approach was chosen as the preferred strategy because it reduces redundant computation by merging the gravity and rotation steps into a single traversal of the grid. This not only simplifies the implementation but also leads to better memory efficiency and cache performance in practice. Even though both approaches share the same theoretical time and space complexity, the optimized method avoids the overhead of creating an intermediate grid, making it more practical for larger inputs. The key insight that made this approach possible was the realization that the effects of gravity and rotation could be combined by directly calculating the destination positions of the stones in the rotated grid. This aha moment was essential in simplifying the overall process. While the brute force method is easier to conceptualize, its inefficiency in terms of memory usage made it less appealing. In contrast, the optimized approach, though slightly harder to implement, is more elegant and avoids unnecessary steps, making it a clear winner. To conclude, the optimized approach strikes an excellent balance between simplicity and efficiency. By carefully handling indices and directly mapping the positions of stones and obstacles in the rotated grid, we eliminate unnecessary intermediate computations while maintaining the same time complexity as the brute force approach. This makes it the most practical solution for the problem. While it may require a bit more effort to implement, the gains in memory efficiency and reduced redundancy make it well worth the effort. Overall, this method showcases how thoughtful problem solving can lead to more elegant and performant solutions, highlighting the importance of combining observations and optimized design in algorithm development. To solve the problem of rotating the box while simulating gravity, we need to break the task into clear steps. First, we parse the input grid, interpreting it as a 2D matrix where each cell contains one of three possible values: dot for an empty cell, asterisk for a stone, or O for an obstacle. For example, consider the input grid shown. It consists of 3 rows and 4 columns, with stones, obstacles, and empty spaces arranged in a specific pattern. Once we have this grid representation, we move to the next step, which is simulating gravity for each column. This involves iterating through each column one by one. For a grid with dimensions m by n, we traverse all n columns, processing each column independently. The idea is to start from the bottommost row of the column and work our way upwards, ensuring that stones fall to their lowest possible positions within that column. As we traverse a column, we use an auxiliary stack or list to temporarily collect stones as we encounter them. Whenever we encounter an obstacle, we place all the collected stones immediately above it, filling the cells below the obstacle with empty spaces. After processing the entire column, any stones remaining in the stack are placed at the bottom of the column, with empty cells left above them. This ensures that all stones in the column have fallen as far as possible, respecting the positions of obstacles. Once all columns have been processed, we reconstruct the grid by filling each column bottom up with the stones and empty cells. The next step involves rotating the grid 90 degrees clockwise. This requires creating a new grid with dimensions flipped. If the original grid had m rows and n columns, the rotated grid will have n rows and m columns. Each cell is then remapped based on the formula. The cell at position I, j, in the original grid moves to position j, m1i, in the rotated grid. This transformation ensures that the rows of the original grid become the columns of the rotated grid, completing the clockwise rotation. Let's focus on some key insights from this algorithm. First, the gravity simulation ensures that stones fall downward until they encounter an obstacle or the bottom of the column. This behavior is efficiently achieved by using a stack to collect and place stones. For the rotation, the mapping formula, I, J, to J, M1I, is crucial for transforming each cell's position correctly. Additionally, the algorithm's efficiency is noteworthy. Simulating gravity for all columns has a time complexity of O(m*n), as we process each cell in the grid once. Similarly, the rotation step also requires O(m*n) time, as we remap every cell. Thus, the overall complexity remains O(m*n). In terms of data structures, the grid is represented as a list of lists, making it easy to access rows and columns. For gravity simulation, a stack is used to temporarily store stones and efficiently manage their placement. The stack plays a pivotal role in simulating gravity. As we traverse each column from bottom to top, stones are collected into the stack. When an obstacle or the top of the column is encountered, the stones are placed in their correct positions. This ensures that all stones settle at the lowest possible positions without violating the constraints set by obstacles. For the rotation, the grid is transformed using the formula I, J, J, M1I. This operation rearranges the grid such that it is rotated clockwise by 90 degrees. It's also important to consider edge cases. For instance, if the input grid is empty, the output should simply be an empty grid. If there are no obstacles, stones will fall to the bottom of their respective columns before rotation. Conversely, if there are no stones, the grid remains unchanged after gravity simulation, and only the rotation step is applied. These considerations ensure that the algorithm handles all scenarios robustly. Finally, there are additional edge cases to handle. If the grid consists of only a single row or a single column, the algorithm must still correctly simulate gravity and perform the rotation. For grids with irregularly placed obstacles, gaps may form between stones in the final configuration. However, the algorithm ensures that stones are always placed directly above obstacles, maintaining the expected behavior. By addressing these edge cases, the solution becomes complete and reliable for any valid input. This structured approach of simulating gravity and rotating the grid ensures that the problem's requirements are met efficiently and effectively. This Python solution for LeetCode problem number 1861, rotating the box, involves two main steps: simulating gravity and rotating the box 90 degrees clockwise. First, the rotate the box function begins by iterating over each row of the input box. For each row, we simulate gravity by allowing stones, to fall to the rightmost available positions while respecting obstacles, *. We achieve this by maintaining an empty slot pointer that tracks the rightmost available position in the row. As we traverse the row from right to left, if we encounter a stone, we move it to the empty slot and decrement the pointer. If an obstacle, * is encountered, the empty slot resets to just before the obstacle. Once gravity has been applied to all rows, we proceed to rotate the box 90 degrees clockwise. This is done by constructing a new grid where each column of the original box becomes a row in the rotated box. We iterate through each column, gathering elements from bottom to top of the column, to achieve the rotation, and append these as new rows to the resulting rotated box. Finally, the rotated box is returned as the output. This solution is efficient, with a time complexity of O(m*n), where m and n are the dimensions of the box, as it processes each cell a constant number of times. Here, we start by defining the method rotate the box, which takes a 2D character array box as input. The first thing we do is to determine the dimensions of the box, specifically the number of rows and columns. Next, we handle the first step, which is to simulate the effect of gravity on the stones in each row. To do this, we iterate through each row of the box. For every row, we track the position of the rightmost empty slot where a stone can fall. We initialize this to the last column of the row. Then, we iterate through the current row from right to left. If we encounter an obstacle, represented by an asterisk, we reset the empty slot to the position just before the obstacle, as stones cannot pass through obstacles. If we encounter a stone, represented by a hashtag, we move it to the empty slot position and replace its original position with a dot. representing an empty space. After moving the stone, we decrement the empty slot to track the next available position. Now that gravity has been applied to all rows and the stones have settled, we proceed to rotate the box 90 degrees clockwise. To achieve this, we initialize a new 2D character array called rotated box with dimensions swapped, columns become rows and vice versa. For the rotation, we iterate through each column of the original box. Within each column, we iterate through every row. We then assign the value from the original box to the appropriate position in the rotated box. Specifically, the value at box, row, col, is placed at rotated box, col, rows 1 row, which ensures the desired 90-degree rotation. Finally, we return the rotated box, which contains the transformed layout after applying gravity and the rotation. Here, we start with the first example where the input box is a 2x4 grid. The goal is to simulate the effect of gravity on the stones, then rotate the box 90 degrees clockwise. For step 1, we process each row from right to left. In row 1, we begin with the rightmost column as the empty slot. As we move left, we encounter a stone at column 0, which we move to the empty slot at column 1, leaving column 0 empty. Along the way, obstacles like the one in column 2 reset the empty slot position. The resulting row becomes #**. Now, for row 2, we follow the same logic, processing from right to left. The stones at columns 1 and 0 are moved to the rightmost available positions, creating the row #***. After processing both rows, the box after gravity appears as shown. Next, we proceed to step 2, where we rotate the box 90 degrees clockwise. This involves constructing the columns of the rotated box by taking elements from the original box in a bottom-to-top order. For column 0, we take the first element from row 2 followed by the first element from row 1, resulting in #**. For column 1, we take the second elements from both rows, resulting in ###. Similarly, for column 2, we gather the third elements, which are both obstacles, to form ****. Finally, for column 3, we take the fourth elements, which are both empty spaces, resulting in ###. Combining these columns gives us the final rotated box. This completes example 1. Now, we move to the second example, which demonstrates a case with no obstacles. The input box is a 2x3 grid. In step 1, we simulate gravity. For row 1, we begin with the rightmost column as the empty slot. The stone at column 2 stays in place, while the stone at column 0 moves to column 1, leaving column 0 empty. The resulting row becomes ###. Row 2 contains no stones or obstacles, so it remains unchanged as ###. After applying gravity, the box appears as shown. Then, in step 2, we rotate the box 90 degrees clockwise. For column 0, we take the first elements from both rows to form ###. For column 1, we gather the second elements, resulting in ###. Continuing with step 2 for example 2, we now construct column 2 by taking the third elements from both rows. This results in ###. Combining all these columns gives us the final rotated box, which is a 3x2 grid. Here, we see that the stones have fallen due to gravity and the orientation of the box has been successfully rotated. With this, example 2 is complete. This example highlights how the algorithm handles cases where the box contains no obstacles, allowing stones to move freely to their lowest available positions. In the third example, we examine a scenario where the box contains only obstacles. The input box is a 2x3 grid filled entirely with obstacles. Since there are no stones, step 1, which simulates gravity, has no effect on the box. The grid remains unchanged as all cells contain obstacles. In step 2, we proceed to rotate the box 90 degrees clockwise. For column 0, we take the first elements from both rows to form ****. For column 1, we gather the second elements, resulting in ****. Finally, for column 2 and step 2, we take the third elements from both rows, which are also obstacles, to form ****. Combining these columns gives us the final rotated box, which remains a 2x3 grid filled entirely with obstacles. This example demonstrates that when there are no stones in the input, the box remains unaffected during the gravity simulation,
and the rotation simply rearranges the obstacles into their new orientation.
This concludes the solution walkthrough for the problem. To analyze the time complexity of our solution, we need to evaluate the algorithm step by step. First, in step 1, we simulate gravity for the stones. This involves iterating over each row in the box, and for each row, processing all columns from right to left. As we traverse each column, the operations performed, like updating the empty underscore slot pointer, moving a stone, or skipping a cell, are all constant time operations. Since we process every cell in the box exactly once, the time complexity for this step is proportional to the total number of cells, which is rows asterisk calls. Next, in step 2, we perform the rotation of the box. Here, we construct the rotated version by iterating through each column of the original box, building rows in the new rotated structure. Again, this requires visiting every cell in the box exactly once, giving it the same time complexity of O, rows asterisk calls. Thus, both steps independently have a time complexity of O, rows asterisk calls. Now, when combining these two steps, we simply add their time complexities together. Since both steps have the same complexity, O, rows asterisk calls, the overall time complexity of the algorithm remains O, rows asterisk calls. Moving on to space complexity, let's first look at the auxiliary space. The algorithm only uses a few variables, such as empty underscore slot and call, all of which require constant space. No additional data structures are created for intermediate computations, so the auxiliary space is O1. However, for the output space, the algorithm creates a new rotated underscore box to store the result. This matrix has dimensions calls x rows, which matches the total number of cells in the original box. Therefore, the output space complexity is O, rows asterisk calls. When we consider both auxiliary space and output space, the output space dominates, making the overall space complexity O, rows asterisk calls. With the combined space complexity established as O, rows asterisk calls, we can now compare this approach to a naive or brute force method. In a naive solution, simulating gravity might involve creating intermediate structures, such as duplicating rows or temporarily reorganizing the matrix multiple times before rotation. While this would still require O, rows asterisk calls, time, it could use significantly more auxiliary space due to redundant operations or data structures. The efficiency of our solution lies in its ability to modify the box in place during gravity simulation and construct the rotated box in a single pass, minimizing space overhead. Additionally, the algorithm's time complexity remains consistent across all cases, whether the input contains many stones, obstacles, or empty cells, because every cell is processed exactly once. This results in a time complexity of O, rows asterisk calls, regardless of the input, and the space complexity remains constant as well. Finally, let's justify the big O notation for our solution. The total number of operations is proportional to the number of cells in the box, which is rows asterisk calls. During the gravity simulation, each cell is visited once, and during the rotation, each cell is visited again. This results in a time complexity of O, rows asterisk calls, since all operations are linear with respect to the size of the input. On the space side, the algorithm's output matrix dominates the space usage. The rotated underscore box has the same asymptotic size as the input box, making the space complexity O, rows asterisk calls. This efficient time and space complexity ensures that the algorithm is well suited for processing matrices of varying sizes without unnecessary overhead. Common mistakes in this problem often stem from missteps in simulating the gravity effect or handling the rotation process. For instance, one frequent issue is incorrectly simulating gravity. If empty spaces aren't managed properly, stones might not stack correctly, leaving them or the spaces in invalid positions. To avoid this, you should iterate from the bottom of the grid upwards to ensure proper stacking. Another common error is rotating the grid twice, before and after applying gravity, when the correct approach only requires one rotation after the gravity simulation. This not only wastes computation but also produces incorrect results. Additionally, it's easy to confuse row and column indices during a 90-degree clockwise rotation. Remember, rows from the original grid map to columns in the rotated grid, and mixing these up can scramble the output. Lastly, edge cases can be overlooked, like grids that are entirely empty, have no stones, or consist of a single row or column. Failing to address these can lead to runtime errors or inaccurate results,
so always consider these scenarios during testing.
Another potential pitfall is inefficient simulation. If you use nested loops to repeatedly drop stones one step at a time, this could result in an n-cubed time complexity, which is highly inefficient for larger inputs. Instead, you should directly compress each column in a single pass, filling it from the bottom up.
This saves time and improves performance.
From an interview perspective, it's critical to recognize that the problem is naturally divided into two sequential steps: simulating gravity and then applying the rotation. Keeping these steps separate simplifies both implementation and debugging. A useful optimization tip is to avoid iterative simulations for gravity. Directly rearranging columns is much faster.
This problem also falls under the category of matrix transformations combined with physical simulation.
Understanding this pattern can help you tackle similar challenges. During testing, always include edge cases such as empty grids, fully filled grids, and irregularly shaped grids to ensure your solution is robust. Additionally, be ready to discuss follow-up variations, like rotating counterclockwise or simulating gravity in different directions, to demonstrate a deeper understanding of the problem.
This problem has strong connections to other LeetCode challenges involving matrix transformations in simulations.
For example, LeetCode 48, Rotate Image, focuses on rotating a 2D matrix in place without using extra space. LeetCode 73, Set Matrix Zeros, involves manipulating matrix elements under specific constraints, while LeetCode 54, Spiral Matrix, explores traversing a grid in a spiral pattern.
Another related problem, LeetCode 289, Game of Life, revolves around grid-based state updates based on predefined rules. In terms of alternative approaches, one option is the direct transformation approach.
Instead of simulating gravity, you can construct the rotated grid directly by iterating through columns of the original grid and filling rows of the rotated grid from bottom to top. While this might be faster for sparse grids, it's slightly harder to implement. Another approach is in-place rotation combined with gravity simulation, which saves space by modifying the grid directly. However, this increases complexity and the potential for bugs. Finally, pre-computing the compressed state of each column before rotation allows you to separate the two steps entirely. This approach clarifies the logic but requires additional memory for intermediate states. Each method comes with its trade-offs, so choose based on the specific constraints and goals of your implementation.
Great job!
To wrap things up, we reviewed the problem, explored the brute force approach, and highlighted key simulation concepts.
Remember, breaking down complex problems into smaller steps is a powerful strategy.
Thanks for watching, and stay tuned for more problem-solving tips.
That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!